Lecture 9. Okay, today I want to demonstrate using Python the following. What happens when we sample? Okay, so as I explained, we save money by not taking the whole census, but by taking samples and drawing inferences from it. But in order to get inference, if you want to draw conclusions from your sample, then you better have a good idea of what happens when you sample, right? So here are some questions that you can ask when you sample. What are the relationship between mean, variance, standard deviation, median, mode of the sample, and of the population? So recall that sampling means you have an entire population, could be like in millions, right? But you don't have the money to get all the data, so you get like a sample of 100 people. And then there are the things that you want to know from the population. You want to know the population mean, variance, standard deviation, the median and mode of the population. And the question is, does it have any relationship with samples, mean, variance, standard deviation, median, and mode? You can ask that question, right? That's the first thing. And these quantities of the population are called population parameters. And these are our core concern. Okay, so these are the items of concern when you think about population. You want to know the population parameters. And the second question is, if the same size n sample is obtained many times, what kind of distribution does the mean have? That one, maybe the question might not so click, but as I show you the Python code running, you might be able to understand what that question is. All right, so let's try. So I wrote a program here. It's not complete, so I'll have to start writing the code as I go. But if I run this, actually, let me just run this much. Okay, so what this code did was len L. So I have 1,600 population data. Okay, it's similar to the number of students in Maritime College, something like that, right? Okay, and then from those people, I measured something, and I got the mean value is shown here. Mean value is 123.05, and the variance is 52367. Standard deviation is 22.8839. Median is 132. So, and this randomly collected data has this M shape. Right? So it's not a bell-shaped thing, right? So you have some data that you're keen to know, you're interested in. However, the data is not bell-shaped, and you want to know the mean value and the standard deviation and variance and all that. Okay. Of course, for us, it's already given to us, so you might ask, why do we care what the sample does? But suppose we didn't know this. Okay. Suppose that these values were not able to be obtained, and we had to figure it out from some sample size. Okay. All right. So let's see what happens if we took oh no, that's not what I meant. If we took some sample from here. So let's say I collected sample size of 10. Okay. Now, I need to explain to you what this means, but let's just collect sample size of 10 and see what we have. Okay. So if I randomly choose from this population, which I call L, and size 10, here are the numbers that I get. I get these numbers, okay? Yeah. Yes. Yeah, just random 10 numbers out of the population, okay? Yeah. Now, what is the average of the above? So let's just copy this much. And if I take the average of that, I get 122.8. And if you remember, the original population is 123.05. So that's pretty good, don't you think? Right? Yeah. And then if I take the standard deviation of this, that's 23.75, whereas the original one is 22.88. That's also pretty good, right? Now let's try the median. Median is 133.5. What was the median here? 132.0. Okay, so that seems to be good. It's not. It's supposed to be bad, but somehow it turned out to be good. Okay, well, what can I do? What about the mode? 134, whereas it's 137. Okay. All right, so this time we got lucky. But let's see. What if I chose a sample, sorry. I chose another sample. So let's say sample is a random 10. Okay. And I try to do print mean of the sample, standard deviation of the sample, median of the sample, the mode of the sample. Let's see what that gives us. Oh, this time the mean value is way bigger. Okay, that doesn't look good. Standard deviation is way smaller, right? The median, I guess it's forgivable. And the mode is 133. Okay, so let's try this again. Okay, so this time, I'm just going to take another sample and print it. Let's see what happens. Then now the mean value, remember the mean value is 123, so this is way less. This is good enough. 107 median, look at this, 107, that's really small, okay? The median that we wanted was something like 133, so this is very bad. Mode still seems to be okay. Let's try to run this again. Okay, 129, that's very off. Okay. And the standard deviation is worse. So what I want you to know at this point is that every time you collect a sample of size 10, you're going to get a different value of the mean, different value of standard deviation, different value of the modes, and all that. Okay. Then the question is, what makes you to believe these sample values? Well, you would believe it more if you took the sample size of 10 and repeated it many, many times, and its mean value becomes close to the mean of the entire thing. Does it make sense? You're taking mean of the means, mean of the variances, mean of the standard deviation, mean of the mode, mean of the median. You take all these values and run it and see what we get, okay? Yes?
So are you, like, for the population that you have, are you basically doing like a sample like over and over again?
Yeah, so what I'm going to do is I'm going to do what I just did here. I just did maybe like 4 times. I took sample size of 10 4 times, right? and sometimes was underestimating, sometimes was overestimating. What I'm about to do is I'm going to do this 1,000 times and take the mean value of all these quantities and see what happens. Okay. Yes.
The standard deviation is the population or sample?
Oh, the question was for the standard deviation, is it population or the sample? Right now, I'm using the population one, so I actually have to Bessel correct it. Okay, good question. All right. So let's see what happens if we actually did this 1,000 times. Okay. And in Python, to repeat something 1,000 times, you have to do a for loop. So this for I in range 1,000 just repeats this procedure 1,000 times. Okay. And every time I do it, I'm going to collect the result of the mean and the variance and all that into these lists. And I'm going to find their mean of mean, mean of variance, mean of standard deviation, and all that. Okay. All right. So what am I finding? Well, the mode somehow is very off. And this happens because sometimes your samples don't have any mode. In that case, it will give you all of them as mode. All the numbers will be as the mode, and then the lowest number is picked. So it kind of, so mode is not so trustworthy here. But look at the mean of the median. Even if you do this 1,000 times, it's pretty bad at figuring out what the median of the sample was, right? So if I go up, the original data had median as 132, and even if I repeated this 1,000 times, it's off by like 4, right? On the other hand, look at the mean, 123.05 and 123.09. I think that's a really good result, right? So you see that the sample, if you repeat it 1,000 times, then you end up with the mean of means being a pretty good representation of the mean of the population. Yes.
What's the probability if you're looking for standard deviation? Because the formula is square root of NPK.
That we can't talk about yet. Okay. Yes.
So, for this procedure, would it be wise to cut out outliers, or does that not matter?
Uh, okay, a good question. If the original population has outliers, should we take it out or not? If it has outliers and the population size is somewhat small, then we should take it out before doing these things. Okay. Um, all right. But let's look at the variance. The variance is 476 from this sample, whereas the original one is what? 523. That's also a very big difference, right? But if you take the variance, and the thing is, this is divided by 10. So if I multiply that by 10 to undo division by 10 and divide by 9 instead, which is the Bessel correction, right? You divide by n minus 1 rather than the entire thing, right? If you do that, you get 529, which is awfully similar to the 523. Okay, you might still say that's quite a big difference. But if you take the square roots, the standard deviations will be pretty similar. Okay, so here's the result that I want to talk about from that first experiment. So the first experiment is what are the relationships between the mean, variance, standard deviation, median, and mode of the sample of the population? And the answer is if the sampling is repeated, the mean values of the sample is a good approximation of the mean value of the population. Okay. So actually, the mean mean value of the sample is a good approximation of the mean value of the population. For variance, you need the Bessel correction. So instead of dividing by n, you have to divide by n minus 1. Good point. Right? Then it's a good approximation. if you take the standard deviation, there's some mathematical glitch there. It's slightly smaller, but we don't really care much. But median and modes are unreliable. It gives you completely different answers, even if you increase the number of times you sample. So the important idea here is that we call the sample mean and the variance as unbiased estimators, which means that it's a quantity that you can gather from the sample. Okay, if you're looking for the median, just getting like 20 people out of the entire student body of SUNY Maritime College is not going to give you a reliable idea of what the median would be. Okay, same thing for the mode. However, if you're looking for the mean value or the variance, then getting those values from the sample is good enough. Okay, so you call these parameters, the mean and the variance, as unbiased estimators. Okay, so that's good to know. Okay, that kind of gives us a limitation of what we can get from a sample. Okay, yeah. All right, so that's the first thing. Now, the second question is, if the same size n sample is obtained many times, what kind of distribution does the mean have? Okay, so let me try to explain this a little bit because the question itself is not so easy to understand. So let me try to explain here. What if I take the sample mean? So let's say I choose, sample size 2. Okay. And then you take the mean value of this. Okay, so let me show you. So for I in range 1000, what I want to do is I want to collect a sample of sample size 2 and append the mean value of those two. So after collecting two, just select two numbers from the population, and then what I want to include in this sample mean is the mean value of the two. I add the two numbers and divide by 2. Just take the average and add them up. Okay, collect them all. Okay, so let's look at the sample mean. Oh, so these are the numbers that we get, but let's plot histogram of the sample mean. Okay, so this is how it looks like. Here's the original one. So here it was like an M-shaped thing, but if you collect two numbers and record its mean, and you do this 1,000 times, you get a 1,000 sample, which looks more close to a bell curve than before, right? Now, do you agree that this would happen? Just try to think why this would happen. So if you take two numbers and calculate its mean, what happens is, like, if you happen to find the big value and a small value, and if you take the mean value, what happens? You get something in the middle, right? So if your original data is widely spread apart, then collecting mean values of two numbers will make the distribution narrower. Does that make sense? Yeah, because it doesn't vary that much. So in fact, the variance changes. So let's see, if I calculate the standard deviation of the original one is 22.88, but if you calculate the standard deviation of this sample mean, it's smaller. Okay, and we actually know how smaller it is. It's if you take 22.88 392, that number, and divide it by the square root of 2, it's comparable. It's very similar. Okay. So if you select size 2 and do this, the standard deviation has the ratio of square root of 2. All right, so if you understood what I'm doing here, let's repeat this procedure with now sample mean being collection of 3 items. So I'm going to do the same thing, but this time I'm going to collect samples of size 3. Exact same thing is done. Okay. Now let's plot the histogram. What is that? That's more like a bell curve, right? It looks more like a bell curve. And not even that, if you calculate the standard deviation of the sample mean, it's now even smaller. But look, if you divide the original population's standard deviation and divide it by square root of 3, they're comparable. Okay. So now let me show you what happens if we do the same thing with this time sample size 10. Or maybe let's make it like 20. All right. Sample size 20. Let's see what happens. Okay. Sample size 20. Now it's really symmetric, right? It's closer to a bell-shaped thing, right? And then the sample mean standard deviation is 4.9855. And what should I divide it by to match this? 10, square root of 10, right? Oh, that varies a lot more than I thought, but it could be. Why does this happen? Maybe it's just simply some sampling error. Oh, it's 20. Sorry. Knew something was strange. Thank you. It was 20. I thought we were doing 10. Okay. All right. So now it's much better, right? Yeah. 4.98 versus 5.11. Okay. All right. So what I'm trying to say here is that if the same size n sample is obtained many times, what kind of distribution does the mean value have? The collection of the mean values become closer to a normal distribution, even if the original population is not normal curve. Okay, that's the important thing. Okay, if you collect a lot of samples and calculate its mean value, even if the original population is not bell curve shaped, the mean value will have a distribution that's bell curve shaped. Yes. Hmm? What?
You would want to use a sample one for standard deviation.
So the question was, when I was comparing the standard deviation, do I use the sample one or the population? The answer is we use the population if it's available, but if you only have the samples standard deviation and to replace the population, then we have to use the sample standard deviation. We'll do an actual example question, and there it will be more clear. Yes.
Go to the slide before. I just want to take a picture. All right, see it.
Okay. All right. So the important thing is the mean values of sample size n follows the normal distribution of population mean mu and the standard deviation sigma divided by square root of n. And this observation, square root of n, that's actually the important thing. Okay, and these are actually all mathematically proven. It's just that to show that it requires a very hard math, so I can't really explain it to you here. But from our experiment, we show that this is indeed what happens. Okay. All right. We can also talk about the distribution of the Bessel corrected. When I say Bessel corrected, it's the sample standard variance, sample variance, or the square of the sample standard deviation. If you collect those values, and if you if you look at the distribution, you get something called the chi-squared distribution. And we're going to use this much later in the course. But today, I'll just throw in the name, but I'm not going to explain anything about the chi-squared. Okay. Now the important thing is, so what do we do from here? Okay. So before exam 1, we were talking about the confidence interval when the entire population is known. Okay? But here we have a different question, slightly related, a similar idea, but here the question is finding the confidence interval of the mean from the sample. Okay, so how do you find the confidence interval for the population mean from the sample? That's basically the question. Okay, and suppose a sample size of n is selected from a population, and from that sample you can find the sample mean x bar, which is different from mu, which is the population mean, and the Bessel corrected standard deviation Sx, which is the sample standard deviation, not the population one. Okay. What is the 95% confidence interval? So what you want to know is that can you speak with 95% confidence that the population mean must be between these two numbers, and you provide two numbers. Can you do that? Okay. That will be a pretty good conclusion you can draw from a sample. Okay. So how do we do it? Well, the basic idea is this. If the sample size of n is 30 or more, then Sx is considered to be a good approximation of the population sigma, and the sample mean follows as we spoke before, the normal distribution of the mu as the mean and sigma over square root of n as the standard deviation. And I explained just by experiment why there's the square root of n there. Now, if the sample size is less than 30, then because Sx is not a good approximation of sigma, we have to use something called a t-distribution. But I'll speak about it if I don't think we have time today, but I'll speak about it tomorrow, okay? But what we do is we do the same kind of calculation as we've done for the confidence interval. You see how we do the z alpha over 2 as the inverse norm of 1 minus alpha over 2, this formula. And for the 95% confidence level, this gives you 1.96. And here's the formula for the confidence interval, right? Your x bar, that the quantity that you have in question, should be locked into these two numbers with 95% confidence. Yes?
In the top formula, are you treating it as a percentile and not a confidence interval?
The question was, am I computing the percentile, not a confidence interval? See, this alpha over 2 gives you the confidence interval because what it's really doing is I'm calculating 0.05 as the significance level. 95% taken out from 100% gives you 5%. But 5% divided by 2, if you do alpha over 2, gives you 2.5%. So you have the 2.5% taken from the 100%, that gives you 97.5 percentile. But that will be actually the place where you want to draw the right side line because you want the confidence interval. So if you go from negative 1.96 to positive 1.96, it's going to capture 95% of the bell curve. Okay, yes?
Is this the one where you're solving for x?
What?
Is this the one where you're solving for x?
Somewhat, yeah, somewhat. Okay, but this is the formula for the confidence interval. Right? This is the formula for the confidence interval, right? It's mu minus z alpha over 2 times the standard deviation. But here I'm not using the sigma over square root of n. I'm instead using Sx over square root of n because Sx is the only information I can get. So it's a good approximation of the sigma. So that's the formula. But now I have to do some algebra here. So the algebra that I have to do is I have to take this one and take only the left side, okay? And I'm going to add this 1.96 times Sx over square root of n to the right side so that the inequality now looks like that, okay? So here I was saying that x bar is between these two numbers, but now you can say mu is less than this number, and you can do the same thing for this right side. You can take this number, and then uh, if you subtract 1.96, if you subtract this to the left side, so let's copy this again. What I'm trying to do is I'm going to subtract this. And you get that mu is bigger than this. So what you end up with is that the population mu must be between these two values. And that's a nice result. So here's the result, okay? So the result is that if you have a sample size of n selected from a population, if the sample mean x bar and the Bessel corrected standard deviation is Sx, what is the 95% confidence level? With 95 confidence, you can say that the population mean must be between these two numbers. How's that? That's a good result, don't you think? Right. Okay, so from here, let's do an actual example. So here's an example. A farm is selling pumpkins, and a buyer wants to know the mean weight of the pumpkins they're selling. So the buyer bought first 40 pumpkins and calculated the mean and variance to be 22 pounds and 4 pounds. You can expect something like this to happen, right? So let's say you're a manager of a big supermarket chain, and your job is to go look for good pumpkins. It's October, and you want some good pumpkins for the Halloween, right? Yeah. So you go to a farmer and you ask, okay, so what's like your average size? And they would say, oh, we sell something like 35 pounds or something, and then you don't trust them. Okay? You want to get some samples and see for yourself. Okay. So what would you do? You buy the first 40 pumpkins and calculate their mean and the variance, and you get 22 pounds and 4 pounds. Right? So the mean value is 22. I think that's really small, much smaller than 35 pounds that the farmer claimed. You can already sense that, right? But maybe you want to get a better idea. Okay, so what's the 95% confidence interval for the mean value of the pumpkins? Okay. All right, so let's see how we can do this. Now I'm just going to use the same z alpha over 2 value that we've obtained before, because that's something that we've done before. So this value would be 1.96 for the 95% confidence level. Okay. All right. Then the next question is, I know that the mu is between, so what was the formula? Let's just copy and paste it. Oh, by the way, I should really change this to z alpha over 2 for future reference, because sorry to change this in the middle of the lecture, but this is better. Okay, so this is the formula I want, and let's apply it here. And in our case, the 95% confidence level is the z critical. By the way, this is called the critical value. So the z critical value is 1.96. So I'm going to use 1.96 there. Well, let's move on. What should we use for x bar? That's the sample mean, right? What goes in here? 22, right? There goes 22. What about SX? 4. That's the sample standard deviation. And what about square root of n? 40. And we can calculate this. Now, you can use this with your calculator, but I don't have my calculator open, so let me just use this one. Okay, so it's 22 minus 1.96 times 4 divided by the square root of 40. That's 20.76. So I get 20.76. 20.76. And let's do the other one, the plus one. If I add it, I get 23.24 because there's a 96, so you have to round it to 24. Okay, so 23.24. Okay, yeah. And there you go. So you can say with 95% confidence, I know that your average weight of the pumpkins is between 20.76 pounds to 23.24 pounds.
How are you getting the 1.96?
Okay, so the question is, how do you get the 1.96? Okay, so just to explain the 1.96, since we have like 5 minutes, let me draw it here. So here's what's happening. You have the normal distribution, the standard normal distribution. Here's 0. And what you're doing is you want to have an interval that's centered around the 0. It's symmetric around the 0, so that you're going to capture 95% of the entire population. Yeah. And the question is, how do you get this? Well, if this is 95%, then how much is this much? It'll be 0.0, not 0.05, because there's the same amount here, so you have to divide it by 2, right? So what do you get? 0.0025, right? Sorry for my awful handwriting. It's hard to draw with the mouse pad. Okay, so you have 0.0025, and what you do is, that means you're really looking at 97.5 percentile. See, this much is 97.5 percentile, right? 5, that's supposed to be 7% percentile. So what you do is you either use your calculator, or you can look at it, and you can get this by saying that Z alpha over 2 is the inverse norm of 0.975, okay? From the standard normal distribution, which is like 0 and then 1 and so on and so on, okay? So you have this, and you get 1.96, okay? Any other questions? Okay, then that's all for today.